Hello everyone, I am Mr. Tan and you are watching Chemistry Tutorial. Let's get into it. For this live stream, I'll be going through the Cambridge International Exam AS and A-Level Paper 1 MCQs for the May and June 2018. So without further ado, let's begin. Question 1. Which feature is present in both ethene and polyethene? Now, ethene is an alkene. So, ethene looks like this. Whereas polyethene is our polymer. Usually, we represent polyethene as follow. Its repeating units will look something like this, assuming we have nth units. So, the bond angles, is it 109 degrees? Does it apply to both of them? No, because the bond angle for ethene is actually 120 degrees, whereas for polyethene is actually 109.5 degree tetrahedral. So A is out. For 2, is pi bonds available for both molecules? Not for polyethene, but it's available for our ethene because there's a sigma bond and a pi bond. But over here, everything is a sigma bond. So that applies. That means for the answer for this question is simply option C. How about D, sp3 orbitals? For you to have sp3 orbitals, that means it must be sp3 hybridized. So only the carbon in ethene is sp3 hybridized. But the carbon in ethene is sp2 hybridized. Therefore, only option C is correct. For question 2, the electronic configuration of an atom of sulfur is 1s2, 2s2, 2p6, 3s2, and 3p4. How many valence shell and unpaired electrons are present in one sulfur atom? Now, in A-levels, we are writing the full electronic configuration as 1s2, 2s2, 2p6, 3s2, and 3p4. But for O-levels, we usually express it as 2.8.6 because 2, 8, and 6. So now, how many valence shell electrons are there? Well, there are 6 valence shell electrons. How many unpaired electrons are there? For this case, let's just refer to the 3s2 and your 3p4 because these are our valence shell electrons. So for s orbital, it can house 2 electrons, so 3s2. Then for p subshell, we have 3 p orbitals. So 1, 2, 3, and 4. Meaning you actually have 2 unpaired electrons. Therefore, the answer for question 2 is D. For question 3, in which pair does the second substance have a lower boiling point than the first substance? For this case, you need to be able to recognize the chemical structures that those substances possess. We have 4 types of chemical structure. They are metallic structure, ionic lattice structure, simple covalent molecular structure, and giant molecular structure. So for question 3, C2H6 is ethane, so it has simple molecular structure, and C2H5Cl is an RX, alkyl halides, is an organic molecule, so it also possesses simple molecular structure. So since they have simple molecular structure, that means we should look at their IDID, instantaneous dipole and induced dipole, which is proportional to the number of electrons per molecule. Therefore, all we need to do is just count the number of electrons present in C2H6 and C2H5Cl. However, usually most of us, we are more familiar with calculating the MR. So there's a positive relationship between the number of electrons and MR. So all we need to do is just count the MR for C2H6 and C2H5Cl. You notice that C2H5Cl actually has a greater MR, so it should have more electrons per molecule. Therefore, C2H5Cl should have a higher boiling point than C2H6. So option A is out. For option B, what we have is an ether. Option B is ether, E-T-H-E-R. And C2H5OH is our ethanol. So both are simple molecules. They possess simple molecular structure, but CH3OCH3, which is the diethyl ether, it has IDIE, but ethanol has hydrogen bonds. So hydrogen bonding is typically stronger than your IDID. Therefore, C2H5OH should have a higher boiling point than your dimethyl ether. So B is out. For option C, we have neon and argon. We can treat them as having the simple molecular structure, although they are atoms, but still is dependent on the size of the electron cloud, or the number of electrons per molecule, which is directly proportionate to the AR, relative atomic mass. Therefore, AR has a greater number of electrons per atom, in this case, than neon, so it will have a higher boiling point than neon. For option D, what we have is CH3NH2, which is an amine. C2H6 is an alkane, and CH3NH2 possesses hydrogen bond versus the IDID that is present in C2H6. So CH3NH2 will have a higher boiling point than C2H6. Hence, the answer for question 3 is D. For question 4, compound J burns in excess oxygen to give carbon dioxide and water only. When a 3-gram sample of compound J is burnt in excess oxygen, 4.4 grams of carbon dioxide and 1.80 grams of water are formed. What is the empirical formula of J? Now, we do not know whether this compound J possesses just carbon and hydrogen, or it possesses oxygen as well. So we are just going to leave it as it is. Instead, we are just going to focus on calculating first the number of moles of carbon dioxide, which is 4.40 divided by 44, because that's the MR of carbon dioxide. So with that, we'll get 0.1 moles of carbon dioxide. Now, the number of moles of carbon dioxide is actually equals to the number of moles of carbon, right? Because 1 mole of CO2 will give you 1 mole of carbon atoms. Therefore, from here, we can actually get the mass of carbon by multiplying 0.1 with the AR of carbon, which is 12. Hence, we actually have 1.2 grams of carbon in compound J. We'll do the same thing for water. So the number of moles of H2O is 1.8 grams over the MR of water, which is 18. And we'll have 0.1 moles of H2O. Now, 1 mole of H2O will give you 2 moles of hydrogen atoms. Hence, the number of moles of hydrogen that we have in this case will be 2 times 0.1 to give us 0.2 moles of the hydrogen atoms. To find the mass, you just multiply by the AR of hydrogen, which is 1. Hence, the mass will just be 0.2 times 1 to give you 0.2 grams of hydrogen. So 0.2 grams of hydrogen present in compound J and 1.2 grams of carbon present in compound J. Now, we are told that the total mass of compound J is 3 grams. So we can actually find out the mass of oxygen in compound J by subtracting 1.2 grams, 0.2 grams from 3 grams. So 3.00 minus 1.2 minus 0.2, and we will have 1.6 grams of oxygen present in compound J. Now we can actually draw our table. Okay. So what are the elements present? We have carbon, hydrogen, and oxygen. That means the options should be that we should consider are option B and option D. Now, so we will put in the mass first. The mass can be in percentage or grams, doesn't matter, because what you want is just a ratio. The mass of carbon is 1.2, the mass of hydrogen is 0.2, and the mass of oxygen is 1.6. Mass over AR is the AR that we need to consider, not MR. So AR of carbon is 12, AR of hydrogen is 1, AR of oxygen is 16. So we find the mole, 1.2 divided by 12, what we have is 0.1, just to double check. 1.2 divided by 12, 0.1, yes. So we have 0.1, this is 0.2, this is 0.1. So we need to find the simplest ratio. Simplest ratio. To find the simplest ratio, we need to divide by the smallest number, which is 0.1. Hence, 0.1 divided by 0.1 is 1, 0.2 divided by 0.1 is 2, 0.2 divided by 0.1 is 2, 0.1 divided by 0.1 is 1. Hence, our empirical formula will be C1H2O1. Hence, the answer is option D. Question 5. The gases X and Y react to form Z. At equilibrium, an equivalent mixture of these three gases is compressed at constant temperature. What will be the change in the mole fraction of Z and in Kp? So let me write out the equilibrium reaction first. So we have gaseous X plus gaseous Y to give us gaseous Z. Now, since this is an equilibrium reaction, that means we need to apply the Le Chatelier's principle. At the same time, there is an equilibrium constant K. In this case, it will be Kp because this is a gaseous system. Now, the Kp is only dependent on temperature. Only dependent on temperature. Since we are told that this equivalent mixture was compressed at constant temperature, that means if temperature is constant, there should not be any change in the equivalent constant Kp. That means we should only consider option B and D. Now, but you notice that the mixture was compressed. So if you are compressing the mixture, in other words, you are reducing the volume. That's why you're compressing it. Since there is a inverse relationship between pressure and volume, where you decrease the volume, effectively you are increasing the pressure. So when you increase the pressure, based on Le Chatelier's principle, the position of equilibrium will shift towards the side so that you can minimize the pressure. That means the side with lesser number of moles of gases, because pressure is proportional to the number of moles of gases. That means the equilibrium will shift towards the right side because there's only 1 mole of gas versus 2 moles of gas on the left side. Therefore, there will be increase in the mole fractions of Z. Hence, the answer is option B for question 5. For question 6, Which gas is likely to deviate most from ideal gas behavior? You need to know the assumptions of ideal gas behavior, and one of the key assumptions is that there is negligible intermolecular forces of attraction. So now we need to check which one has the greatest intermolecular forces of attraction. Notice that your HCl, helium, CH4, and NH2, they possess simple molecular structure. So therefore, we will need to consider their ID. And strength of ID is dependent on the size of electron cloud or the number of electrons per molecule. So if you check the MR, strictly speaking, we should just look at the number of electrons per molecule. However, since there's a positive relationship between the number of electrons per molecule and the MR, for convenience sake, we can just look at the MR. Therefore, just count the MR and notice that HCl has the greatest MR. Therefore, the answer for this is just A. For question 7, the enthalpy change of reaction is minus 114 kilojoules per mole. So you need to know that this is actually the standard enthalpy change of neutralization. Per mole refers to the per mole of water produced. So for reaction 1, 2 moles of water was produced. Therefore, that means for every mole of water produced, it releases 114 over 2 kilojoules of energy. So if you check the reaction 2, you have 2 moles of H2O. Bear in mind that barium hydroxide is a strong base, HCl is a strong acid, so strong acid, strong base will give you a value of negative 57.3 because 114 divided by 2. But here we have 2 moles of water, so therefore the answer will just be 114 kilojoules per mole of that equation. Right, I want you to know that for every mole of water produced for strong acid, strong base reaction, we will produce 57 kilojoules of energy. For questions 8, sulfur reacts with concentrated nitric acid in a redox reaction. What are the changes in oxidation number of sulfur and of nitrogen in this reaction? The oxidation state of sulfur, so let me just write this down first. S plus 4HNO3 to give you SO2 plus 4NO2 plus 2 H2O. So sulfur has an oxidation state of 0 because anything in elemental form, it has oxidation state of 0. But over here, it's plus 4 because oxygen takes a charge of minus 2. And 2 of them, so to balance it out, this must be plus 4. So the change in oxidation state of sulfur is plus 4. How about nitrogen? Nitrogen oxidation state is plus 5 because hydrogen is plus 1, oxygen is minus 2, so it's plus 5. But the oxidation state of nitrogen in NO2 is plus 4, so there's a difference of minus 1. Hence, the answer for question 8 is option D. Let's look at question 9. Materials can be classified by their chemical structures. 4 common types of structure are metallic, ionic, simple molecular, and gel molecular. Some physical properties of 4 substances are shown in the table. Which substance has a simple molecular structure? Simple molecular structure typically cannot conduct electricity because for you to conduct electricity, you must have mobile charge carrier. So for simple molecular structure, their charge carrier is the electrons which are involved in forming the bonds, such as covalent bonds, so they are not available to conduct electricity. Therefore, they must be poor conductors of electricity. Hence, for question 9, you should only consider option B and D. However, we also need to realize that simple molecules that adopt simple molecular structure, they tend to have a lower melting point. Hence, option B will be your answer. For question 10, in a particular reversible reaction, the yield of product is increased. If the temperature is increased, if the pressure is decreased, which equation could describe this reversible reaction? Now, if the temperature is increased and yet the yield of product is increased, that means the forward reaction must be endothermic. Why is that the case? Let me just use a very simple example. Let's say A gives you P, and this forward reaction is endothermic. That means in the formation of product, actually there is an absorption of heat energy. That means there will be a drop in the temperature. So I'm just going to put a cold at the product side. I'm just going to put a hot at the reactant side. So if the temperature is increased based on Le Chatelier's, this is a reversible reaction, sorry about that, because it's reversible, so they apply Le Chatelier's principle. So when the temperature is increased based on Le Chatelier's principle, the equilibrium will shift towards the side that is lower in temperature. So that if this is towards the side with the lower temperature, and it happens that the side with the lower temperature belongs to the product side, therefore this forward reaction must be endothermic. Hence, you should only consider option A and D. However, we have one more point, which is if the pressure is decreased, the yield of the product is increased. Now, if you just consider option A, you notice that on the left side, we have 2 moles of gaseous molecules. And on the right side, you have 4 moles of gaseous molecules. So if the pressure is decreased, based on Le Chatelier's principle, the position of equilibrium will shift towards the side so as to increase the pressure, which means that you will favor the side with more moles of gas. And it happens that the side with more moles of gas belongs to the product side. Hence, for question 10, the answer is option A. For question 11, a chemical company used a catalyst in a chemical process. The company has now decided on not to use the catalyst, but to increase the temperature so that the rate of the reaction is the same as it was when the catalyst was used. Which statement about the new conditions compared to the original conditions is correct? Now, previously, was there any use of catalyst? There was a use of catalyst, but now there wasn't any use of catalyst. Hence, we know that the catalyst actually provides an alternative pathway with a lower activation energy. Now that we are removing the catalyst, so the activation energy must have increased because now you are using the, this is the y-axis is of energy, the x-axis is actually the progress of the reaction. So over here, this is your uncatalyzed reaction. This is activation energy for the uncatalyzed. This is the activation energy for the catalyzed reaction. Now that we are removing the use of catalyst, that means now the reaction pathway will proceed like this with a higher activation energy. Hence, B is your answer. A is wrong. But yet, why do we reject option C and D? That's because the increase in temperature matches the rate that was produced, when the catalyst was used. And we know that since there is a match between the rise in temperature with the catalyst in terms of effect, hence the number of successful collision per unit time remains the same. Rate is what? Per unit time. Therefore, C and D are wrong. So the number of successful collision remains the same actually. Hence, for question 11, answer is option B. Oops. For question 12, which oxide does not react with cold dilute sodium hydroxide to produce a salt? For option A is an aluminium oxide, so it's an amphoteric oxide, and we know that amphoteric oxide can react with both acid and base, in this case sodium hydroxide. For option B, P4O10, This is an acidic oxide because it's non-metal oxide, so an acidic oxide will react with a base. For C, sulfur dioxide, SO2 is an acidic oxide, so it will also react with a base. For D, silicon dioxide is actually also an acid oxide. However, SO2 actually you can think of it as sand. For it to react with sodium hydroxide, it must be in concentrated form. That means SO2 can only react with concentrated sodium hydroxide. Dilute sodium hydroxide is not sufficient in itself. Therefore, the answer for question 12 is D. For question 13, the graph shows trends in 4 physical properties of elements in period 3, excluding argon. Which graph has electronegativity on the y-axis? Now, as you go across the period, in this case period 3, electronegativity will increase across the period. If you recall, fluorine is the one that is the most electronegative elements. So electronegativity will increase across the period. Therefore, the answer is option D. For question 14, in this question, X represents an atom of chlorine, bromine, or iodine. Which explanation for the variation in volatility now down group 17 is correct? Now, as you go down the group, the melting boiling point actually increases from chlorine to iodine. Bear in mind that these halogens adopt simple molecular structure. That means they possess intermolecular force of attraction, or IDID, which stands for instantaneous dipole-induced dipole, which itself is dependent on the size of electron cloud or the number of electrons per molecule, or the MR, relative molecular mass. So as you go down the group, the MR increases, the number of electrons per molecule also increases. This is the one that explains why there is a variation in volatility down group 17. If you understand that, then the answer is obvious, and it will just be option A, because IDID, instantaneous dipole-induced dipole, between molecules become larger. For question 15, to manufacture cement, 1,000 million tons of limestone are decomposed each year. To manufacture lime for agriculture, 200 million tons of limestone are decomposed each year. So, what is the chemical formula for limestone? The chemical formula for limestone is just calcium carbonate. So, if it undergoes thermal decomposition, it will produce calcium oxide plus carbon dioxide. Now, we know that to find the mole, the mass has to be in grams, but in this case it's okay because we are asked about the mass of carbon dioxide in tons. So it's okay. So therefore, let's find out the number of moles of calcium hydroxide that was being used, which is actually 1,200 million tons, because 1,000 million tons plus 200 million tons divided by the MR of calcium carbonate. So you need to refer to the data booklet. So I'll just use the AR of calcium as 40. Okay, I'll just use the AR of calcium as 40. So 40 plus 12 plus 16 times 3, so it's just 100. Of course, some data booklets will use the AR of calcium as 40.1, but it's okay. So 1,200 divided by 100. So what we have is technically 12 moles of calcium hydroxide. I put an inverted, open inverted, close inverted commas. Now, notice that based on the equation, the mole ratio of calcium hydroxide to carbon dioxide is in a 1:1 ratio. That means the number of moles of carbon dioxide is also equals to this 12 moles. To find the mass, all we need to do is just use the mole multiplied by the MR of carbon dioxide, which is 44. So 12 times 44, what we have is simply 528 million tons of carbon dioxide. Hence, the answer is option B. For question 16, in group 2 of the periodic table, the properties of the elements and the compounds show regular change down the group. Which property shows a decrease from magnesium to barium? For option A and B, we have the decomposition temperature of carbonates and nitrates. However, the explanation for both is the same. Let's just use carbonate as an example. So if you compare magnesium carbonate versus barium carbonate, we are going to use this explanation, which is, as you go down the group, the charge density actually decreases from Mg2 plus to Ba2 plus, because charge density what is charge density? Charge density is actually represented by Q plus over R plus. Q plus represents the charge of the cation ion, R plus represents the ionic radius. So the charge for Mg2 plus and Ba2 plus is the same, all right? So this Q plus is the same. But the thing is, as you go down the group, this Ba2 plus has a larger ionic radius, larger size as compared to Mg2 plus, due to the increase in the number of quantum shell, screening effect, etc. So if the denominator is larger, that means this whole thing is smaller. So if the charge density is smaller, so the charge density is actually smaller for Ba2 plus ion. Now the thing is, if you look at Mg2 plus, if Mg2 plus has a higher charge density, it will be able to distort and polarize the electron cloud of the anion, either the carbonates or the nitrates, more effectively, which also means that it's able to distort or weaken or polarize the CO bond in carbonate, the CO bond in carbonate, or the NO bond in nitrate. So let me just use a simple arrow pushing mechanism. So the thing is, because this has very high charge density, technically it's able to weaken this bond actually due to the pooling effect, because there's a pooling effect, technically speaking. So the bonds will be more easily cleaved, weakened, or polarized. So if Mg2 plus can polarize the CO bond by itself, then it doesn't need an extra helper. That means the thermal decomposition temperature need not be high. Hence, the thermal decomposition temperature actually increases from magnesium to barium. Therefore, option A and B are wrong. Now, some students may ask, why am I using charge density to explain the thermal decomposition temperature or the melting point of those salts? Why can't I use lattice energy? Well, if you use lattice energy, it will give you a different observations, in terms of explanation. However, we can't use lattice energy to explain the phenomena of this decomposition temperature for this group 2 nitrates or carbonates. That's because lattice energy is only strongly applicable for strongly ionic compounds. Magnesium carbonate or magnesium nitrates, these are not strongly ionic compounds. How do you tell if a compound is strongly ionic? Well, the anion cannot be polyatomic anion. What do we mean by polyatomic? These are polyatomic anions. Polyatomic means, poly means many atoms. So over here you have many atoms. You have 4 atoms. So if something is polyatomic, if the anion is polyatomic, we cannot use a lattice energy to explain. So over here we have to use a charge density to explain. So A and B are out. For C, well, as you go down the group, group 2, the solubility of hydroxide actually increases. The solubility of the carbonates actually decreases. And the solubility of the sulfate actually decreases as well. The reason has to do with delta H solution equals delta H hydration minus lattice energy. Right? This phenomenon can be explained using this equation. So the only correct answer is option D. For question 17, when concentrated sulfuric acid is added to solid sodium bromide, bromine gas is produced, along with a number of other products. However, when concentrated sulfuric acid is added to solid sodium chloride, only hydrogen chloride and sodium hydrogen sulfate are produced. What is the reason for this difference? Now I'm just going to write the equation first. So we have NaCl plus H2SO4 to give you, right, this is solid, liquid because it's concentrated. Right, this you must use concentrated, it cannot be a dilute aqueous acid. So you have NaHSO4 solid plus HCl gas. This reaction is highly exothermic, so you actually get steaming fumes of HCl. If you use sodium bromide instead, what you have is simply this one first. This is your first step, right? Solid, liquid to give you NaHSO4 solid plus HBr gas. However, the HBr gas can further react with H2SO4 liquid to give you Br2 gas, bromine gas, plus SO2 gas, plus your H2O liquid or gas in this case, because if it's highly exothermic, we're going to get steam. So how do you compare this? Well, if you know that Br minus, halides are actually reducing agents, right? Because we know that I minus, right, Ki is a strong reducing agent. So therefore, versus Cl minus. Now bear in mind that concentrated H2SO4 is actually an oxidizing agent. Because if you check, this has oxidation state of +6 in H2SO4, but this has oxidation state of +4 in SO2. So if it gets reduced, itself is an oxidizing agent. So technically speaking, what we have over here is actually a redox, whereby this serves as an OA, oxidizing agent, and this serves as an RA, a reducing agent. So actually, I minus is a more powerful reducing agent than Br minus, then Cl minus, then F minus in terms of the reducing agent, reducing ability. However, if you talk about oxidizing ability, then I2 will be weaker than Br2, then Cl2, then F2. You notice is always the opposite. If something is a strong reducing agent, it'll be a weak oxidizing agent, so on and so forth. Hence, the answer for this question is just option D, because the bromide ion is a more powerful reducing agent than the chloride ion. Now for question 18, the dative covalent bond can be represented by an arrow, and the arrow points towards the atom receiving the lone pair. So this is how we draw our ammonium ion, which is, well, NH3, right? This is a Lewis base, okay? A Lewis base or a Bronsted-Lowry base. So there is a lone pair, and it's going to donate this to hydrogen, H+. So we put a plus outside because technically what we have is NH3 plus H+ to give you your NH4+. So the lone pair comes from the nitrogen. So we cannot choose option A and B. So we should only consider option C and D. However, we must choose option C because ammonium is NH4+, not NH4-. But we do have NH2- actually, and this is actually called amide. Do not confuse this amide with the organic amide, which looks something like this. This is organic amide, but this is the inorganic amide. So sometimes we can be using the same name, but it can represent different things. For question 19, this is a little bit tricky. Now, sulfur dioxide can be catalytically oxidized by an oxide of nitrogen in the atmosphere. Which reaction shows the regeneration of the catalyst? So what we have is that, or perhaps I'll just go to the option D so it's easier to explain this. Now look at it this way. You have SO2, okay? In this case, our oxidizing, or in this case, this is a reducing agent. So what we have is an oxidizing agent. And we know that an oxidizing agent itself will be reduced. So now, what we have is actually reducing agent versus oxidizing agent. A reducing agent itself will be oxidized to produce SO3, and the oxidizing agent itself will be reduced to give you NO. So in this case, this is your catalyst. This is your catalyst. So if you want the catalyst to be regenerated, because now in this case, after a reaction, we are actually getting a deformed, technically, with inverted comma, a deformed catalyst. So you need to regenerate it back. To regenerate it back, you need to oxidize it back, right? Because NO to give NO2. So in that case, that means if you look at option A, B, C, D, we need to actually choose option A and D only. Okay, based on this example, if you see. Now, in this case, we have to choose D because NO gets oxidized. We are not going to choose option A. Okay, we need to choose our option D. Because if you choose option A, then your equation is going to look something like this. That means you are actually using SO2 plus NO2 to give you what? SO3 plus N2. You notice that no matter what you do, you can't really balance this equation. Hence, the answer for question 19 is option D. Now let's look at question 20. Now for compound Y, okay, compound Y is treated with an excess of hydrogen gas in the presence of nickel catalyst. The product is fully saturated. Now we know that in this case, this is a catalytic hydrogenation process. Now don't confuse this with electrophilic add, because some people thought that when you add hydrogen to alkene, and we know that the main reaction for alkene is electrophilic add, but it's not. In this case, this is a catalytic hydrogenation. It's different from electrophilic add. And why is that the case? Because it requires a catalyst. So it is a heterogeneous catalysis. Heterogeneous catalysis. So now, after you add hydrogen, what we have is that your alkene is going to get reduced. So where are our chiral carbon atoms? Well, there's one over here. 1, 2, 3. We have another one, which is 4. Okay, but where's our fifth one? So let's check again. Yeah, the fifth one is actually over here. So we have 1, 2, we have 3, we have 4, we have 5 over here. All right, so in such questions, you just have to be a little bit careful with the counting. Now for question 21, which equation represents a valid propagation step in the chlorination of ethane? Now in the chlorination of ethane, you only get an alkyl radical or a halogen radical. You never get a hydrogen radical. That's also a reason why hydrogen gas was never spotted in the FRS, free radical sub of alkene. So if you see option A, there is a hydrogen radical, which is not possible, because if you do have hydrogen radicals, then we should expect to see hydrogen gas being evolved, because in the termination step, H dot plus H dot gives you H2. So option A is out. Option C is also out. Option D is out because option D is a termination step, it's not a propagation step. So by the rules of elimination, the only reasonable answer is just B. Now for question 22, malic acid is used in the food industry and for stabilizing drugs. It is the cis isomer of butene dioic acid and has a structural formula of so and so. What is the product formed from the reaction of malic acid with cold dilute acidified manganate plus 7 ions? Now, in this case, your butene dioic acid actually has 2 key functional groups, which is the alkene and the carboxyl group, or some people call it the carboxylic acid group. So when you add cold acidified KMnO4, you're actually trying to perform an oxidation process or a mild oxidation process. So only your alkene functional group will be subject to mild oxidation to form a diol. That means you must have 2 OH. So you just look. A, B, C, D, which one has 2 OH? Oh, you have 2 OH over here, OH and OH. And this OH must be next to each other on consecutive carbon atoms. Is there any 2 OH here? No. There's only 1 OH here. Here, there's no OH. I think there's a carbonyl group. So based on elimination, you notice that only reasonable answer is just A. So there's really no need to draw up the full structure. So the answer for 22 is A. For question 23, For question 23, primary halogeno alkanes undergo hydrolysis reaction. Now, in this case, the hydrolysis that we are referring to is actually the addition of aqueous sodium hydroxide. That's a hydrolysis process or nucleophilate substitution. Since this is a primary halogeno alkane, we should expect an SN2 reaction. Now, which reaction will occur most rapidly if they are all warmed to the same temperature? Now, because this is an SN2 reaction, okay, so if you write the SN2 reaction, so this is going to be our rate equation. It means rate is equals to K, which represents the rate constant, Rx, as well as our nucleophile. So that means the rate, this is SN2 reaction because it's first order with respect to Rx and first order with respect to the nucleophile. Hence, the overall order is actually 2. Hence, we have SN2 reaction. That means the rate is actually dependent on the concentration of both the Rx and the nucleophile. Now, in this case, we assume that the concentration is the same for nucleophile. That means what we need to focus is actually the nucleophilicity of the nucleophile involved. And we know that basicity parallels nucleophilicity. What does it mean? Well, let's just use H2O and OH minus as an example. Which is the stronger base? OH minus is a stronger base. So OH minus is a stronger base. At the same time, OH minus is a stronger nucleophile. That's why there's a direct relationship between basicity and nucleophilicity. Therefore, for question 23, we should only consider option B and D because H2O is a weaker nucleophile than your hydroxide ion. Now, as mentioned over here, now in the SN2 reaction, if you draw the mechanism, so for SN2 reaction, okay, by the way, I should use a stereochemical formula, but I'm just going to use a very general way of just drawing. So there's an atom of the nucleophile on this electron deficient carbon, and there's a halogen over here. So there's going to be a simultaneous forming of this C nucleophile bond as well as the breaking of the CX bond. So that means you need to have the CX bond being weak so that it's easier to cleave it, so the rate will be able to proceed much faster. So therefore, if you compare CBr versus CCl bond, which bond is stronger? This bond is stronger. What we want is a weaker bond, which is this case here, so that the rate of hydrolysis will be much quicker. Hence, the only correct answer is option B for question 23. Now, next one. For question 24, structural isomerism and stereoisomerism should be considered when answering this question. A colorless liquid C5H11Cl exists as a mixture of two optical isomers. When heated with sodium hydroxide ethanol, a mixture of only two alkenes is formed. What could the colorless gas be? Now, C5H11Cl, if you calculate its DU, its degree of unsaturation, is 0, which means that it's a fully saturated alkyl halide. Now, when you heat it with sodium hydroxide ethanol, you are trying to perform an elimination process. Do not confuse this with sodium hydroxide aqueous, because sodium hydroxide aqueous will give a substituted product as the major product. So over here, we have elimination product, so we will get alkene. Now, let's see how to do this. Let's consider option A then. Okay, option A. All right, so question 24. Let's see why A is wrong. Because HCl and you have C2H5, C2H5. They told us that this C5H11Cl exists as a mixture of two optical isomers. That means you have actually two enantiomers. That means you must have one chiral carbon because 2 to the power of n. Right? If you have one chiral carbon, you're just going to get two optical isomers, enantiomers. So let's check. Do we have any optical? Do we have any chiral carbon in option A? You don't have any. This is not a chiral carbon because you have two identical groups attached to this same carbon atoms. All right. So therefore, for option A is out because option A does not exist as a mixture of two optical isomers. Let's consider option B. Now, same thing actually for option B, let's see. So we have CH3, CH2. I'm just going to use a skeleton. CH3, CH2, CH2. Then there's a C here. Okay, there's a CH3. Right, so CH3, CH2, CH2. Now there's a Cl over here. Right, CH3, CH2, CH2, C, Cl, H, CH3. Now, does it have a chiral carbon? Yes, it does. There's a chiral carbon. So that means it fulfills the first criteria that it exists as a mixture of two optical isomers. However, if you try to perform elimination, do we get only two alkenes? Well, let's try. You have this over here because there's an invisible H. You just remove it, so you get this. Do you have any cis trans over here? No, you don't, because you have two H that's connected, two identical group attached to this carbon. So there's no cis trans. So over here, there is no cis trans over here. But you do have an alkene. Now let's assume that now you have another H here. You eliminate your Cl and H over here. What you have is this. Oops. Okay, let me just check. Oh, there's no H. I don't want to confuse myself because, yeah. Okay, so this is what we have. Let me just draw this again. So what we have is this, all right, and this. So this is the other alkene, but does it have cis trans? Yes, it does, because there's a H here, there's a H here. Although this is a CH3, this is a C2H, but it doesn't matter. It's just that the correct name we should call is that they are called E and Z isomers, but it's still part of cis trans isomerism. We do not need to have, let's say CH3 and CH3 here and H to qualify it as a cis trans isomer. You can have, for example, let's say this one. Cl, Br, I, and H, for instance. As long as for each carbon atoms, you have two different groups attached to each carbon atoms of the alkene, it will qualify as a cis trans or geometrical isomers. So over here, you have 1 and 2 because you have cis trans over here. So you actually have 3 possible alkenes. Hence, option B is out. Now, for option C, let's see. Okay, so what we have is C, CH3, CH3, and then we have a H here. Oops. Okay, then we have a C, H, Cl, C, H, H, and H. Okay, so if you remove the chlorine and the H over here, so there's going to be a double bond. But because this carbon has two identical groups, so there's no cis trans, but there's an alkene form. Over here, if you have a H here, there's a H and a Cl, remove it, you're going to have an alkene. There's no cis trans because you have two identical groups on these carbon atoms. So 1 plus 1 gives you 2. So therefore, do we have any chiral carbon? Yes, we do. This is the chiral carbon because this carbon is attached to 4 different substituents. You have a hydrogen, you have this whole alkyl group, you have a chlorine, and have another methyl group. So therefore, the answer for question 24 is C. Let's look at option D then. We have CH3, we have CH2, C, Cl, okay, then we have CH3 and CH3. Now, it does not exist as a mixture of two optical isomers because this itself is not a chiral carbon. So we don't even have to look at the next step whether it can produce a mixture of alkenes, two alkenes. So answer for 24 is option C. For question 25, when warm water is added to halogenal alkane X, an SN1 reaction occurs. SN1 occurs for tertiary substrate, tertiary RX typically, right? So silver nitrate is then added and a yellow PPT is formed, which means that we should expect to have iodine present in the RX because AgI is yellow PPT, AgBr, silver bromide, is cream PPT, and silver chloride, AgCl, is a white PPT. So just look for the option with iodine in RX. That means we should only consider option B and D. Yet, why do we reject option B? Well, let's see. For question 5, if we look at option B, I'm just going to use a skeleton. Methane, ethane, propane, butane. So it's a 4-carbon group, RX. So what you have is iodine over here. So you have 1 iodobutane. Notice that this is a primary substrate, primary RX, so it should undergo SN2 and not SN1. But if you look at option D, all right, propane, methane, ethane, propane, so 2-methyl, 2-iodo. So you notice that over here, this carbon is actually linked to 3 alkyl groups. So this is a tertiary RX. So it will undergo SN1. Therefore, the answer for question 25 is option D. For question 26, which alcohol will react with an acidified solution of potassium dichromate to produce a ketone containing 6 carbon atoms? Now, first, you want to count the number of carbon atoms in all the 4 options. Now, butane, you have 4 carbons, right? So, methyl is 1, but you have 2 of them because dimethyl. So, 4 plus 2 is 6. So, okay, we can keep this option first. Pentanol, 5 carbon atoms. Methyl, 5 plus 1 is 6. Penta, 2 dimethyl. Penta is 5, right? But the thing is, we have dimethyl, that means 1 plus 1. So, 5 plus 1 is 7. But we want to have 6 carbon atoms. So, option C is out. Last one, pen plus methyl, 5 plus 1 is 6. So, we can keep A, B, and D. But we rule out option C because option C has 7 carbon atoms. Now, so for it to acidify it to form a ketone, that means it must be a secondary alcohol. So, in fact, from option A, when you see something that's Bu1 or something is 1 or, it's understood that it's a primary alcohol. So a primary alcohol will never produce a ketone. It will produce an aldehyde or a carboxylic acid. So option A is actually out. Let's just consider option B and D. Now, for option B, question 26, I will just draw the skeleton, right? Methane, ethane, propane, butane, pentane. So 3 O, that means you have OH as the third carbon, and 2-methyl. Notice that this carbon is linked to 2 carbon atoms. So this is actually our secondary alcohol. Okay, let me just cancel this out to avoid confusion. So this is a secondary alcohol, which means that secondary alcohol can be oxidized to a ketone. Right, so answer is B. But let's see why D is wrong. Methane, ethane, propane, butane, pentane. So over here, but we have 3-methyl. That means this carbon is actually linked to 1, 2, 3 different alkyl groups. That means this is a tertiary alcohol. A tertiary alcohol cannot be further oxidized, even if you use a stronger oxidizing agent such as potassium permanganate. Hence, question 26, answer is option B. For question 27, which statement about butanol is correct? Now, look at the last 3 letters. The last 3 letters is O, that means this itself is a ketone. Alright, so sometimes from the last few letters, you can actually know which functional groups or hormonal series it belongs to. For example, let's say I have butane, so ANE is alkane, butene is alkene. You have OIC, that means it's a carboxylic acid, or AL, which is aldehyde, OL, alcohol, so on and so forth. Now back to the question. So which statement about butanol is correct? Butanols can be dehydrated by concentrated sulfuric acid. That's not possible. It can only be, for you to dehydrate using concentrated sulfuric acid, it must be an alcohol. So I can use excess concentrated sulfuric acid at 170 degrees Celsius. But butanol is a ketone, it's not an alcohol, so option A is out. Option B is also out because Tollens reagent is a test for aldehydes. Now the chemical formula for Tollens reagent is actually diamine silver, which looks something like this. Alright, you have 2 ammonia ligands to 1 Ag+, so the coordination number is actually 2. So option B is out because it will give a negative test with Tollens reagent, but it can give a positive test with Brady's reagent, which is otherwise commonly known as your 2,4-dinitrophenylhydrazine, 2,4-DNPH. Now, for option C, butanol reacts with HCN. That's possible, but it proceeds via a mechanism. The name is called nucleophilic addition and not electrophilic add. Electrophilic add is for alkenes. So C is out. For butanol to react with sodium boron hydride, that's possible because it can get reduced. In fact, butanone, being a carbonyl, can get reduced by hydrogen gas, lithium aluminum hydride, sodium boron hydride, and so on and so forth. But let's check. So let's see how do we draw butanone. Methane, ethane, propane, butane. Alright, you cannot put a carbonyl group at the terminal end because otherwise what we have is an aldehyde. You can either put at this port or this port, but they are equivalent. So this is our butanone. Now if you were to reduce it, alright, so hydrides, right, just use a simple mechanism. So there's a nucleophilic attack by the hydrogen ion. So what we have looks something like this. We get alkoxide. Okay, there's a H over here. Then you protonate it. So this is our alcohol. And it gives us our secondary alcohol because this carbon atom is linked to two different carbon atoms. So this is a secondary alcohol. Is this alcohol chiral? Yes, it is, because there's a H here. This carbon is chiral because it's linked to four different substituents. You have OH, CH3, H, and an ethyl group. So for question 25, the correct answer, or rather for question 27, the correct answer is option D. For question 28, okay, ethanol is used to make product R in a three-stage synthesis. The first stage that we have, if the question ever asks you to identify the name, okay, the type of reaction that there is, then the first one shall be our nucleophilic addition. Once you perform nucleophilic add, what you get is actually our cyanohydrine. That means you have an OH and a CN. So let me just draw this out so you can see what I'm trying to say. So we have a CH3. Personally, I actually more comfortable using skeletal, but in case you are not familiar with it, I will just do the full display formula. So this is your ethanol. You have a HCN, right? So you have CN minus, perform nucleophilic attack, right? So what we get is actually an alkoxide, CN, but you got to protonate. This is actually what we call a cyanohydrine. Cyano because you have a CN, hydrogen because you have OH. Now if you add your H2SO4, you're actually trying to perform an acidic hydrolysis. And this acid hydrolysis is going to affect your nitrile, your CN group. And we will have CH3, COHH, and a COOH. Because your CN gets hydrolyzed to form COOH. Now notice that the question is saying that you add concentrated sulfuric acid. Now, if you use excess concentrated sulfuric acid at 170 degrees Celsius, we're going to get a dehydration of alcohol. So there's a possibility that there's a dehydration of alcohol. However, this is not a dehydration process or elimination process because the question told you that only a few drops of concentrated sulfuric acid is added. This few drop is equivalent to saying that it's a catalytic amount. Usually, catalysts are added in small quantities. That means what happens is that this is going to be an esterification process. Esterification process because you actually have a OH group and a carboxylic acid group. That means you can form an ester. Of course, the question also told us that an ester is formed. So let's look at the chemical formula of this particular species, product Q. So we have carbon 1, 2, 3. So we have 3 carbons. How many H do we have? 3, 4, 5, 6. 6H. O, 1, 2, 3. So you have C3H. Sorry, let me check again. How many O's? We have 3 O's. Yeah. C3H6. What am I saying? Sorry again. C3H6O3. C3H6O3. This is what we have. But the final product, okay, it actually told us that 2 molecules of Q, this is your Q, okay, react to give 1 molecule of R, and this R is an ester, plus 2 molecules of water. Now, if you recall, to form an ester, to form 1 mole of ester, you actually produce 1 mole of water. And if you get 2 molecules of water, that means, okay, you need 2 molecules of Q. So if you have 2 molecules of Q, so 2 C3H6O3. Technically speaking, we have C6H12 and O6. Okay, because 3 times 2 is 6, 6 times 2 is 12, 3 times 2 is 6. But then you remove 2 molecules of water. And 2 molecules of water means you actually remove 4H and 2O. 4H and 2O from this species. Hence, we have C6, H12, right? It minus 4H, you get C6H8. Over here, 6 oxygen minus 2, where you have is O4. You simplify, the empirical formula will be C3H4O2. You see? So this is how we get this answer. I know some students try to use a mechanism method. Yes, I mean you can use that. However, this is a simpler method. Don't forget this is an MCQ question. So you try not to spend too much time on the single question. So by using this shortcut method, you'll be able to get your answer much quicker, a lot quicker. Now for question 29, the ester ethyl butanoate can be hydrolyzed using an excess of dilute sodium hydroxide. Now first, you need to know what are the reactants used to make this ester. Now how do you know what are the reactants used to make this ester? Well, to make an ester, we need to have an alcohol and a carboxylic acid. Of course, you can use an acyl chloride, but for this case, I'll just say that you need a carboxylic acid. So you need an alcohol and a carboxylic acid. And the first name that we have, ethyl, represents that of an alcohol. The second one represents that of a carboxylic acid. So ethyl means you need ethanol. Butanoate means you need butanoic acid. That means for question 29, we can actually use an ethanol plus butanoic acid to form the ester. Okay? Now, so similarly, that means if you were to hydrolyze this ethyl ethanoate, we are going to get ethanol and butanoic acid. Now, but you are performing this hydrolysis via sodium hydroxide. So the butanoic acid is going to react with sodium hydroxide. Your ethanol will not react with sodium hydroxide. All right. If you want to form, let's say, options such as C itself, you need to make sure you use sodium metal so that there will be a redox reaction occurring between alcohol and sodium metal with the evolution of hydrogen gas. Now that you know that butanoic acid will form, and butanoic means you have 4 carbon atoms, right? Methane, ethane, propane, butane. So you look for the one with 4 carbon atoms, and the only one is option A, right? CH3, CH2, CH2, COH, which will react with sodium hydroxide to form your salt. So therefore, the answer for question 29 is option A. For question 30, this one we need to refer to our IR spectrum, which is our infrared spectrum. Now I notice that actually from 0 until around 1000 onwards, actually these are what we call the fingerprints region. That means these are like your alkyl, those CH3, CH2, all those fingerprint regions. The key thing we need to focus on is actually from around 1000 onwards, 1000 wave number onwards. Now, the thing is, do you notice that there's a very sharp peak at around 1007? So this sharp peak actually tells us that there's a carbonyl group. There's a C double bond O, carbonyl group. So for question 30, there is a carbonyl group present. And this carbonyl group actually is that of the aldehyde and the ketone. So that means we should search for the one with a ketone or an aldehyde group. Well, A is out, B is out, C is a ketone, it's a propanol, D is possible because there's a CO over here, so it's a ketone. So that means we should only consider options C and D. However, now you check, there's a wave number of around 3001. Now this is where you need to refer to your data booklet, right? Because this one is not that broad. The hydrogen bonds of this species, right? Those molecules that are able to form hydrogen bonds, right? They tend to form, as in their peak will be much broader, but this peak is not that broad. It's quite sharp. So therefore, you cannot consider option D already. Hence, the answer for this is option C. Now let's look at the next question, question 31. Now, for complete combustion, 1 mole of an organic compound X requires 2.5 moles of O2. Which compound could be X? Now, for this case, for this question, no choice. We have to consider everything. So let's say C2H5OH plus O2. Well, organic compounds will give you carbon dioxide and water as your product. So you just do a balancing from here. So you have what we have here, 6H here. So that means you have 3. 4 plus 3, 7. 7 minus 1. So it's 6. So that means you need to have 3 O2. That means option 1 is out already. If option 1 is out, that means the only answer is just 2 and 3. Right? You can always prove it to yourself. C2H2, right, plus O2 to give you CO2 plus H2O. Right? You have 2 carbons, so you're going to put 2 here. You have 2H, so this is fine. So 2 times 2, 4. 4 plus 1, 5. So this will be 2.5 O2. So option 2 is correct. Option 3, okay, you don't try to, I mean, you can just put a CH3CHO, but sometimes it may be easier to just put it as C2H4O. All right, then plus O2 to give you your CO2 plus H2O. How many carbon you have? 2. How many H you have? 4. So you put a 2 here. So 2 times 2, 4. 4 plus 2, 6. 6 minus 1, 5. So this is also 2.5 O2. So therefore, 2 and 3 are correct. For question 32, in which pairs do both species have the same number of electrons? Now, the thing is 35Cl and 37Cl are actually called isotopes. Isotopes are atoms of the same element with the same number of protons as well as electrons, but different number of neutrons. So option 1 must be correct. For option 2, 35Cl minus 3517Cl minus. 17 protons, 17 electrons, but because there's a minus 1, so actually it has 17 protons and 18 electrons. Argon is 40, 18 argon, so same number of electrons. Because this is electrically neutral species, 18 protons, 18 electrons. So option 2 is correct. For option 3, we have 40, 18 Ar, 18 here, alright. But for potassium, you have 40 K, right? So let me check for potassium. I think it's 19, yeah, 19 K. That means it actually has 19 proton, but 18 electrons because now 1 electron is lost, so that it carries a +1 charge. So 18 electrons, 18 electrons. Hence, 1, 2, 3 are correct. Now for question 33, the only correct answer for question 33, for which reactions does the value of standard enthalpy change, delta H, represent both a standard enthalpy change of combustion and a standard enthalpy change of formation? Now only option 1 is correct because for option 1, we can consider this as standard enthalpy change of combustion of carbon, because combustion of carbon means you burn, okay, you combust 1 mole of carbon in the presence of excess oxygen to form CO2. So for option 1, we can call it standard change of combustion of carbon, standard enthalpy change of combustion of carbon, as well as the standard enthalpy change of formation of 1 mole of CO2. Because the definition of standard enthalpy change of formation of 1 mole of CO2 is that the energy changed, enthalpy changed, when 1 mole of product is formed from its constituent elements at the standard conditions. And the elements used to form CO2 are carbon solid and oxygen gas. Option 2 is out because you have 2 moles of CO. That's one thing. You must be 1 mole of the product, not 2 moles. At the same time, you cannot call this enthalpy change of combustion because to combust carbon, you should get CO2 and not CO. CO is, to form CO, this is a incomplete combustion. For option 3 is also wrong because yes, you are forming 1 mole of CO2, but it's not from its constituent elements because carbon monoxide is a compound. So for question 33, only option 1 is correct. For question 34, now the temperature of a reversible gas phase reaction is increased. Since it's a reversible reaction, that means we may have to apply Le Chatelet's principle. Which statements are always correct? More product is formed at equilibrium. Well, this statement is not always correct. Why is that the case? Well, let me just write this equation. A plus B. Okay. Let's say that this is a endothermic process. As I mentioned earlier, if this endothermic process, that means we can just treat the product side as cold and the reactant side as hot. So is it or so if the temperature is increased, yeah, if the temperature is increased based on the Charteris principle, the position of equilibrium is going to shift towards the side that will favor the production of more heat. In this case, it will favor the side that removes the heat. In other words, the colder end. Right? So yes, in that case, we have more product being formed at equilibrium if the forward reaction is endothermic. However, if the forward reaction is exothermic, then actually the reactant side will be more favored. Therefore, since the question is asking us which statement is always correct, then we cannot choose option 1 because option 1 is only correct some of the times. Now, if 1 is out, then the obvious choice is just 2 and 3. However, let's go through the option 2 and 3. When the temperature is increased, yes, the average speed of the particles will increase. That's a fact, because now it possesses more energy to move about quicker. At the same time, there's also more successful collision per unit time. Yes, because when you increase the temperature, you actually increase the average speed of the particles. They can move faster, which leads to the higher probability of having more successful collisions, so that reaction will occur. This is in line with the collision theory that we learned in A level. For question 35, okay, so okay, Cl2 plus H2, all right, Cl2 plus H2 to produce 2 moles of HCl. Now we have 0.710 grams of Cl2. So what you need to do is you need to mass over MR 0.710 divided by 35. Because it's a 1:2 ratio, okay, so once you know the moles of Cl2, multiply by 2, multiply by the mass of HCl, you'll be able to get exactly 0.730 grams of HCl in the first reaction. So statement 1 is correct. Now for statement 2, you need to know the equation, the reactions between Cl2 plus NaOH. In the cold conditions, this is how the equation looks like. Cl2 plus 2 NaCOH to produce NaCl plus NaClO plus H2O. Okay, so we have same thing. We have 0.710 grams of Cl2 divided by MR to get the number of moles of Cl2. Then for NaCl, because it's in a 1:1 ratio, right? So the number of moles of Cl2 will be equivalent to the number of moles of NaCl. Multiplied by the MR, you get a mass, and the mass will be exactly 0.585 grams. So statement 2 is also correct. Now, this one is in cold conditions. I want you to know that the oxidation state of chlorine, in this case 0, over here is -1, over here is actually +5. So in fact, this is actually this is actually +1. In fact, this is actually what we call a disproportionation reaction. And disproportionation reaction itself is a redox reaction. It's just that it's a single species serving both as a reducing agent as well as an oxidizing agent. For option 3, at hot conditions, what we have is another disproportionation reaction, Cl2 plus NaOH. But this time around, we produce NaCl, but instead of NaClO, we get NaClO3 plus H2O. Now let's try to balance the equation. So we have 3Cl2, 6 NaOH, 5 NaCl, and 3 H2O. So now what we have is find the number of moles of Cl2, but because it's 3:5 ratio, so we need to do appropriate multiply by the appropriate coefficients, the constant, to get the actual mole of NaCl. Multiply by MR of NaCl, you get a mass, and it turns out to be 0.975 grams. Let me just do this using a calculator to show how it works. Now, 0.71 divided by MR of chlorine, which is 71, because 35.5 times 2 So this is what we have. However, 3:5, right? So you need to divide by 3 times 5. Divide by 3 times 5. This will be the number of moles of sodium chloride. Multiply by the MR of sodium chloride, which is 23, the A of sodium plus 35.5. So notice we get exactly 0.975 grams. Hence, statement 1, 2, and 3 are all correct. For 36, solid barium oxide is added to some ammonium sulfate solution in a test tube, and the mixture is warmed. A piece of damp red litmus paper is held over the mouth of the test tube. Which observations will be made? In O levels, we know that an ammonium salt can react with a base to produce salt, ammonia gas, and water. So it should come as no surprise that barium oxide is actually a base. In fact, when barium oxide dissolves in water, BaO plus H2O, you actually get BaOH2. BaOH2 is a very, very strong base, equivalent to that of sodium hydroxide or potassium hydroxide, for instance. So now, since we have a base here, and we have ammonium salt in the form of ammonium sulfate, the gas produced is actually ammonia gas. So statement 1 is correct, because ammonia gas, NH3, will react with water to produce NH4 plus OH minus. That's the reason why you need to moist the litmus paper, because without the water, you will not be able to get a hydroxide ion, which will cause the litmus paper to turn from red to blue. Now, what is the identity of the white PPT form? Well, your barium, what we have is that, let me just write the ionic equation. It will just be barium ion, Ba2 plus a sulfate ion to form the white PPT, which is barium sulfate. So the white PPT is actually your barium sulfate. A brown gas is evolved when with strong heating. Now that's not true. The brown gas, one example of a reaction that can give you brown gas that I can recall is actually a sodium nitrogen dioxide. For instance, let's say we are trying to decompose things such as barium nitrate. So if you decompose barium nitrate, you're going to get things like barium oxide plus NO2 plus oxygen gas. This itself is actually a brown gas, but we do not have any nitrate over here. So statement 3 is out, and the only correct answers are statement 1 and 2. Let's look at the next question. Oops. Oh, 37. Yeah. 37. Which compounds show geometrical or cis-trans isomerism? Now, for a molecule to have cis-trans isomerism, A, B, X, Y, you must not have two identical groups attached to either one of these two carbon atoms that are involved in the CC double bond. So based on this logic, you see that actually option 1, 2, and 3 are all correct, right? Because if you check for option 1, you have what? CH, CH3. You have CH3, C2H5. Now I understand that some people may not think that this is a cis-trans because they thought that, oh, I must have CH3, CH3, and this must come in the form of H. But it's okay. In fact, this is what we call E and Z isomers. E and Z actually comes under umbrella of geometrical isomerism. Geometrical isomerism, you actually can break it up into two parts. For instance, you have a cis-trans, your typical cis-trans, and your E and Z. Alright? But the key thing to note is that you must not have two identical groups attached to each of these two carbon atoms that are involved in the CC double bond. So by that logic, 1, 2, and 3 are all able to exhibit geometrical isomerism. For question 38, which pairs of compounds may be distinguished from each other by testing with alkaline aqueous iodine? Now this is a test for organic species with either this moiety, you have a HOHCH3. Now some students ask, what do I mean by moiety? Well, let me spell it out. MOIETY. It's just a a more specific type of functional groups. Now bear in mind that now this thing here, this carbon must be connected to either a H or a C. Alright, because I think a lot of school teachers don't really mention that. This must be either H or C. Because if let's say this happens to be for instance, let me just use a very simple example. If let's say over here this is an N, then it will not be able to give you a positive test with this alkaline aqueous iodine, otherwise known as a haloform test or the triiodomethane test, because it will give you a yellow PBT, which is CHI3. This is our yellow PBT. Alright, if it's an N, this reaction will not occur. It will not generate your yellow PBT. So this must be either a C or H, a carbon or hydrogen. Now that you understand this, now there's another thing that you need to take note is that the simplest primary alcohol that will give you a positive triiodomethane test is ethanol. Simplest secondary alcohol will be propan 2-ol. Of course, you can actually draw it out and see for yourself. But if you know these examples, you'll be able to solve your questions a lot quicker. Okay, the simplest aldehyde will be ethanol. The other one will be your propanone. Notice ethanol can get oxidized to ethanol. Propan 2-ol can get oxidized to propanone. Right. To understand why that's the case, you might want to refer to the mechanism. Right. In organic chemistry, mechanism is the ABC to understanding organic chemistry. Now, so therefore, let's look at the options. Option A, right, ethane, 1,2-diol. Oops, let me just put a H now, so it's easier for you to see. Okay, there's no CH3, right? But we know that ethanol, okay, it has this moiety, at the same time it's linked to a H. So only your ethanol will give you a positive test with alkaline aqueous iodine for option 1. For option 2, propan 2-ol. As I mentioned earlier, propan 2-ol looks like this. This is an alcohol, methane, ethane, propane, because you have 3 carbons. 2 because the OH is attached at the second carbon, so it's propan 2-ol. So you have this moiety and you have a H, and you have a carbon here. This carbon is linked to this carbon, so it will give you a positive test. It will give you a yellow PBT with alkaline aqueous iodine. But how about methyl propan 2-ol? Well, 1, 2. Let me see. Propan 2-ol, right? Methane, propane, yeah. So there's a CH3 here, CH3 here, CH3 here. Okay, but we have OH. Okay, so that means this is another CH3. Right. So as you can see here, there's no H. We need to have this as a H, but there's no H. It's all CH3. So methyl propan 2-ol will not be able to give you a positive test. Now let's look at the option 3. Now we already mentioned earlier, ethanol will be able to give a positive triiodomethane test, but how about butane 2-ol? Well, actually I'm more comfortable using the skeleton because it's a lot quicker. I'll encourage students to learn how to use skeleton. So methane, ethane, propane, butane. So this OH. Notice there's a CH3 here, there's a H here. So therefore, it has the moiety that we are looking for, and this is a carbon. Therefore, both ethanol and butane 2-ol will give you the positive test, and you are unable to distinguish them from each other using this test. Hence, the answer for question 38 is 1 and 2. Let's look at the next one, question 39. The diagram shows an experimental setup which can be used in several different experiments. Which process could be demonstrated by using the above apparatus? Now we cannot use this setup for the oxidation of ethanol, because to oxidize ethanol we need to use KMnO4, which is a liquid, an aqueous solution. But notice that over here, yes, we do have a liquid X, but the thing is, if you put your KMnO4 over here, let me check. This liquid X is ethanol, yeah. If you heat the ethanol, what happens is that ethanol is going to get vaporized. But this thing itself has to be our KMnO4. You cannot oxidize ethanol using silica or alumina. So 1 is out. If 1 is out, that means the option has to be 2 and 3. But let's check. Dehydration of ethanol. There are actually a few ways to dehydrate alcohol. One of them is to use excess concentrated H2SO4 at 170 degrees Celsius. However, because we are using concentrated H2SO4, at the same time, we are raising the temperature to 170. So there could be a safety concern involved, right? Because right now, your H2SO4 will be fuming. It's very dangerous. So usually people adopt a safer approach, which is to use this setup as shown in the diagram. What happens is that you use Al2O3 to dehydrate ethanol. Now you'll be asking, how does the dehydration alcohol gets carried out using alumina? Now let me use a very simple example to explain. The typical alumina that we use is actually Al2O3. Now we do agree that actually your Al3 plus, okay, let's try to visualize this. Your Al3 plus is actually high charge density. That means, typically speaking, it actually generates some H plus ion. It's actually quite acidic, so to speak. Whereas your O2 minus is alkaline, so it's actually a bit alkaline. So just visualize this way. Because this Al3 plus is acidic portion, it's going to remove the alkaline side. That means this Al will remove the OH, whereas this O2 minus will remove the H. So they help to complement each other by removing H and OH. So this allows the dehydration to occur. Right, I'm using a visualization method to show you how the dehydration occurs. Now, for option 3, cracking of paraffin. Paraffin is actually a hydrocarbon. In fact, it's actually an alkane. And we know that we can actually crack alkane. We can either perform catalytic cracking or thermolytic cracking. So in this case, we have a cracking using catalytic cracking because the catalyst involved is our alumina or silica. So option 2 and 3 are both correct. Now for question 40, we have an ester that can be made in a school or college lab by a sequence of 4 reactions or fewer using compound Z as the only organic material. Now, first you need to count the number of carbons present in the ester. We have 6 of them, because 2 plus 1, 3, 4, 5, 6. So we have 6 of them. Now, this is an ester. To form an ester, we need an alcohol as well as a carboxylic acid. Now, if you are just going to use a single compound Z, that means over here you have 6 of them. Alright, so first thing I'll be thinking of is that 6 divided by 2, you see. So you're going to have 3 carbon atoms per molecule. But that kind of thinking is a little bit abstract for some of the students to understand. So let's just consider all the options so it's easier to follow me. Now what we have is actually methane, ethane, propane, propanol. Okay, 3 carbons. Right, so you have propanol. So you can actually oxidize this propanol to give you propanoic acid. And propanoic acid will react with propanol because it's ester and carboxylic acid reaction to give you an ester. 3 plus 3 gives you 6. Right, so meanwhile over here, for this aldehyde, we can actually reduce this aldehyde. This is our propanol. Reduce this aldehyde to propanol, oxidize this aldehyde to propanoic acid, and combine the reaction, these two species, propanol, propa1-or to be precise, with propanoic acid. And when they react, it will give you the ester. In fact, this ester itself is called our propyl propanoic because it's generated by propanol and propanoic acid. This is not possible because this is a ketone. In fact, this is propanone. If you were to reduce it, we will get a secondary alcohol, the propan-2-or. And we know that to form an ester, you need a carboxylic acid. So to form a carboxylic acid, you can only work with a primary alcohol. So even if you reduce it, you can only get a secondary alcohol, and the secondary alcohol can only get oxidized to a ketone and not to a carboxylic acid. So therefore, option 3 is out. So I've completed the analyzing all the 40 questions. So that's it for now. If you like this video, subscribe and hit the notification button so that you don't miss any of my future chemistry videos and live streaming. Talk to you soon. Peace out.